the climate is a function of a living organism, its physiology. We're just barely beginning to understand how this planet actually works and the role of life in maintaining climate. You know, climate, when people used to talk about climate, they spoke of a hot climate or a cold climate, but they just as often spoke of a wet climate or a dry climate. So when we say climate change is affecting rainfall patterns, we should actually be saying the changing rainfall patterns, that is climate change. That's not a result of climate change. All the time, you know, if you read a news article on emissions, carbon or something, they'll have a photograph of like this cracked field. You know that photograph, right? You've seen it all the time. That is actually not caused by global warming, but the implication is that it is. So the implication. So who benefits from this? In fact, the fossil fuel companies are fine with the standard narrative of climate change, and they are investing heavily in biofuels, plantations, and carbon sequestration, carbon capture technologies, and geoengineering. So you got to look at where the money's going and who gets empowered by which narrative. So the water narrative, that's not I mean, you could say, well, okay, if we're going to talk about one substance, let it be water, not carbon. But water is very different. It's not globally more or less evenly distributed. It doesn't lend itself very easily to modeling. And the way to restore water depends on a million and a billion local place-based solutions that involve not just humans, but all life.
When people think of the water resource of precipitation, they consider that it's a gift from the gods and you get the water, but that is not true. There are at least 3 components that contribute to precipitation in any one place. And as you move down to the mid-latitudes, you find that you have 3 components. One comes from the oceanic evaporated water, which is what everybody thinks. There is a regional component. In the case of the Mediterranean seas, water evaporated over the Mediterranean. And then there is a local component that is the one that governs, for instance, the presence or the development of storms. And the problem is that people normally think of the water resource as something that is given, and it's not the case. What we found is that if you change surface properties in places where the atmospheric circulations are limited, you stop contributing with the evaporation, and you increase the temperature of the air mass, and the result is that you lose storms. So this applies to a number of regions around the world. And once you trigger the changes, they propagate, they have threshold or tipping points, so that if you degrade the land past a certain level, the local precipitations disappear altogether. That's probably what happened in the Mideast and a number of other places. Once you desiccate the wetlands and you cut the trees and so on, eventually you turn into a desert, and it can be explained very well.
Basically, the planet has been here for 4.6 billion years, and for over 4 billion years, we've had water covering most of its surface. And that water, through its basically unique heat properties, governs some 95% of the heat dynamics of this blue planet. And it's then a whole sequence of water processes that regulate and have regulated the Earth's climate, including through the natural greenhouse effect, which has warmed the Earth's surface 33 degrees centigrade, warmer than it would otherwise be. And of course, it's that warming through the natural greenhouse effect that's actually allowed us to keep liquid water on the planet, has allowed life to evolve, and of course, it makes Earth habitable and such a unique, special place. CO2 is also a component of that heat dynamics, but it represents less than 4% of that heat dynamics through its component of the greenhouse effect. It's basically our focus exclusively on just the greenhouse gases, and that 4% of the heat dynamics regulated by the CO2 greenhouse component, that's in a sense defocused us from the real facts, the fact that 95% of the heat dynamics is regulated by water. And of course, we have massively influenced the amount of water and those processes through our degradation of our land systems. And when you come back down to all the basics, you're really looking at pedogenesis, the actual primary formation of soils. And really, how did then soils form? And they only formed 420 million years ago. Prior to that, we didn't have life on land, but it was actually the microbes breaking down mineral rock to make soils that allowed biosystems to be formed. And of course, with those biosystems, with those soils, we developed hydrology, and with that, the whole terrestrial biosystem and the terrestrial global hydrology and the global climate. As we change the land, we change the hydrology, and in that process, we change the heat dynamics of the blue planet.
And of course, around the world, we've got wildfires, we've got algae blooms, we've got desertification, et cetera, that are all basically a failure of the soil sponge. So one way to think of the soil sponge is that it's another word for healthy topsoil, which can go quite deep. And I have a demonstration that I like to do that kind of gets right down to the details here. And I do this with a simple plate of flour that is a stand-in for the sand, silt, and clay that is the mineral substrate of all soil. And let's see what happens when we rain on a landscape that does not have a soil sponge. So anyone who's done any baking knows that what happens when you put water onto flour is that the water is running off. It's not actually going in to this. And if this was a landscape, of course, this water is moving sideways rather than down into the landscape. And you can see it's creating a flood around the edges. A lot of erosion is happening. If this was a hilly landscape, we'd get mudslides. And of course, the water in this landscape now has got everything. It's got the soil in it, but it also has any chemicals that were being used on that soil or any nutrients going down into the lakes and streams and rivers. So what do we need to do to turn flour into bread, or to turn sand, silt, and clay into a soil sponge? We need to add biology. So in the case of bread, we're adding yeast, but in the case of soil, we are adding all of the biology that makes up a healthy topsoil. So once we've done that, all of those little particles have stuck together, and suddenly they have a structure. And that structure has structural integrity. So like a kitchen sponge, if you stuck it into water, it doesn't fall apart. But it also has porosity. And so when we rain on this landscape, something very different happens. So when we're raining on the soil sponge, it's soaking up the water. That water is getting down to the plant roots. Even if this was a very sandy soil, actually the structure of this is going to hold that water at the level of the plant roots. So whether you start with a heavy clay soil or a sand soil, turning it into a sponge and creating that pore space and adding that organic matter and that life, it's going to make a big difference. Typically with this demonstration, I can add about 9 times as much water before it starts flooding at all. But the flood that happens is really different. the flood is coming out from the bottom. So this is refilling the springs, refilling the aquifers. It's being filtered as it moves through the landscape. It's being filtered both physically and biologically. And we can keep raining on this, and it's holding it in that in-soil reservoir for later use. And then it's very slowly evaporating and transpiring through the landscape to cool the landscape. So I like to ask people, if you lived somewhere with just a little bit of rainfall, which landscape would you rather have around you? And I typically would say this one, the soil sponge. And if you lived somewhere with a lot of rain, you'd still rather have this landscape. So in either case, we want the sponge.
So here in the shade of diverse, rich vegetation of different ages, of different types, with roots at different horizons, soil is kept cool and moist. And so like a moist sponge, when the rains come, it just sucks it all up. It feeds into the earth, and it returns as springs, creeks, rivers, keeping the water clear and cool. And then what happens, as the sun evaporates moisture off the ocean, the water vapor drifts inland. This water vapor can't actually condense as clouds and fall as rain without a nuclei to form around. And then one of the most important ones is hygroscopic microorganisms. These are microorganisms produced within the stomatal cavities of trees and the underside of the tree leaves, released into the atmosphere, and around these microorganisms, it allows that water vapor to condense into a liquid and to fall as rain. Now, as that process happens and water undergoes that phase change from vapor to liquid, it goes from very large to very small. And so it creates this void that needs to be refilled by more humidity. And so this is a system called the biotic pump. This is how moisture moves from the oceans through the Earth's continents. The trees are actually seeding the moisture, and then as the moisture is seeded and falls, it actually drives more moisture into the system. And so this is, you look at the Amazon rainforest, for example, actually feeds water through the rest of the continent, not just the rainforest itself. If you destroy the rainforest, you destroy the pump, and you destroy the rainfall patterns in the other areas.
We could understand the changes. The vegetation was lost. All of the rainfall caused the sediments to go into the lake. And then the temperatures on the surface were vastly higher. And with these temperatures, what happens is, there is a term in ecology, probably you all know about this, is called evapotranspiration. Well, that is the conflation of two different measurements. Respiration, plant respiration mainly, and evaporation. By fixing the aquatic situation and working from the coast, increasing seagrasses, reed beds, increasing the evaporation, changing the temperature differentials, removing the sedimentation, and bringing the sedimentation onto the shoreline, and then growing grasses, shrubs, and trees, we can change the surface temperatures. We can begin to hold the moisture in the lower atmosphere. And when we do this, we can turn the winds around. And if we do that, we will bring back the moist air, which would then cause a complete change. It's not a localized impact.
If we could turn this around to what's out there that we can nurture, that would be a really good way to go. And then in terms of how our thinking is, so we've been hearing about degraded landscapes, post-flood landscapes, and desertified landscape. So many people would see these images in the news or descriptions of these in news reports and think, this is a result of climate change. And the immediate response is disempowerment, sadness, grief, helplessness. But if we start to understand and make this shift to understand that these are also the causes of climate change, that the desertified landscape where the water is evaporating or flooding and removing topsoil, where you're losing the carbon because the soil is uncovered and it's oxidizing, and all of understanding these dynamics, that once we understand that that's a cause of climate change, then we can begin to address these landscapes and be more empowered and include others in this work. Where I see some positive is that there's this bringing together of understanding. The way people are talking about it isn't that climate is over here and biodiversity is over here, and we have to kind of, deal with one and then deal with the other. That there's a growing understanding that these are very much tied together. So many people don't know that restoration of our landscapes is possible. So let's get that word out there.